And as a result, I thought I wasn't going to get a chance to deliver the talk, but I'm very fortunate to have the chance now to deliver it here at International Space University. So thank you, Ante, for helping make this possible. So for those who don't know me, my name is Max. I am an aerospace engineer at Maven Space, which is a company at the NASA Ames Research Center dealing with in-space manufacturing and space resources. I previously worked for the NASA Ames Research Center for SpaceX, and my background, my undergraduate background, is in astrophysics, but my graduate focus and my professional focus has been in space resources and aerospace engineering. This topic here, the topic of space elevators, is by far the thing that makes me the most giddy. It is very far from practical, I will freely admit that. But in terms of the scale of just what makes me the most peppy and excited to talk about versus what pays the bills, this is definitely the thing that makes me the happiest. So I'm really excited to talk to you about today because it also combines space elevators, something I love very much, with Mars, the planet I am most interested in exploring and the planet I'm most interested in seeing humans get to. And because what I want to pitch today is kind of the reason why space elevators, while we usually focus on them as tools for Earth, there are reasons to believe that the first one to get built isn't going to be built here. Will probably be built on another body, and I would argue in this case that other body is going to be Mars. So just a quick review of the basics of a space elevator, so we understand the basic concept. It is not a tower. There's a common misconception that you build a space elevator by stacking structural elements on top of each other until you've built it up high enough to reach space. That's not what it is. It is not a tower going up. It is a tether coming down from the synchronous orbit altitude. What you do is you construct a factory in synchronous orbit about 35 kilometers above the ground, and then you start building a tether downward and upward simultaneously, so the center of gravity is always staying at the synchronous orbit altitude. Eventually the tether reaches the surface and about 50,000 kilometers out into space. Once this is done, you can take a conventional elevator, something with electric motors and solar panels, no rockets involved, start from the surface of the Earth and then very slowly climb up the tether just for the price of electricity. So no explosive rockets, no expensive rocket propellant, no massive infrastructural investment on the ground. All you need is something that can electrically climb this tether. Once it reaches the end of the tether, all you do is let go. Because remember, everything above synchronous orbit, there is an effective there is centrifugal force that makes this direction, outward, feel like it's down. So once you're above synchronous orbit, all you have to do is let yourself fall to a higher altitude. And if you let go at various points above the synchronous orbit, you can be sent to higher orbits. You can be sent interplanetary, to Mars, to the asteroids, even outside the solar system if your elevator is long enough. And the advantage to this is it means that you can capitalize on the available energy of the rotation of the planet to get payloads to other places in the solar system. It only costs the cost of electricity to haul the payload up, which means that you can capitalize on the efficiencies of electric systems. A motor being driven by a solar panel can be 30 to 60% efficient, can be very efficient. Contrast that with a rocket, which is never more than 0.1% efficient at best. So that is how you get a vast reduction in launch costs for getting hardware to space. Quick history of the subject. It's a very old idea. It was proposed in the 1860s. But when it was originally proposed, there was no material anywhere close to the required strengths in order to make the concept possible. However, gradually over time, we developed an understanding of a material called carbon nanotubes, which have a theoretically high enough strength-to-weight ratio that would allow us to produce something like a space elevator. We currently have the ability to manufacture carbon nanotubes that are strong enough to do this. The problem is they're only a few millimeters long. The challenge we're fighting is not to find the right material, it's to find a way to scale up production to make 10,000 tons of it or so, the amount required in order to manufacture a tether. Yes?
You want to reduce lighting?
Can you read it?
Right. No, the lighting.
Is that better? I know you're eating, I don't want to turn your lights off.
Okay.
Can everyone read this all right?
Yeah.
So the ideal won't become feasible when we have strong enough materials. We already have strong enough materials. The idea will become feasible when someone figures out how to manufacture enough of those materials at an economic scale. And when will that be? Who knows? Experts can predict anywhere from the 2030s to the 2060s. No one knows. It requires predicting breakthroughs in materials science, which is incredibly difficult to do. However, the argument, even though we don't know exactly when this will be feasible, we do know, based on the feasibility criteria, that it will always be more feasible in certain places compared to other places. And that's the argument that this kind of rests on. So once the tether is built, you develop this infrastructure all along the length of the tether, climbers, electric climbers that use solar panels to climb up to higher altitudes, apex station where a counterweight is located, lets the tether be manufactured from a little less material. The infrastructure is kind of deployed along the tether as a way to enable this. So getting into the math just very briefly, I'm not going to dwell too long on this. The material has to be self-supporting. And there are two forces that are acting on the material. There is the downward force of gravity, which falls off as radius squared. And there is the effective centrifugal force of the tether being whipped around the planet, which goes up with radius. So the combination of those two forces means that there is a peak in the effective stress right at geosynchronous altitude. And as a result of that, the tether itself can't be a constant thickness. The tether has to bulge. It has to start thin, bulge thicker, reach a maximum thickness at geosync altitude, and then taper off to an infinitely thin cross-section. And you can avoid making it infinitely thin by adding a counterweight. So what we can do is we can break out, though, the terms of this equation based on whether they're planet properties, which I've highlighted in red here, or material properties, which I've highlighted in blue. And by investigating how these properties in red change by looking at other planets, we can quantify the feasibility of the space elevator around other bodies that aren't the Earth. Oh yeah, of course, please feel free to take pictures. And we quantify this with something we call the taper ratio. So the taper ratio is the ratio of areas between the point of maximum thickness at synchronous altitude and the minimum thickness at the surface of the planet. Everything about the elevator's feasibility can be expressed in terms of this taper ratio. If the taper ratio is enormous, then the amount of material in the tether is enormous and unmanufacturable. The smaller the taper ratio is, the more realistic it is to build it. So what are some actual values then for the taper ratio? Well, in theory, and I emphasize in theory here, you can manufacture a space elevator out of literally any material. It's just the taper ratio will become enormous. For example, with steel, I don't know if you can read the scale here, but this goes by 5 times 10 to 206th power millimeters. So yes, you could manufacture a space elevator out of steel, it's just it would be 170 orders of magnitude wider than the observable universe. Even as an astrophysicist, that's stressing the definition of in theory to me. But if we just make, say, a factor of 20, let's say we improve the strength to weight ratio of our material by just a factor of 10, that takes us into the region of Kevlar. The taper ratio changes drastically. It only becomes a taper ratio of about 10 to the 8. So at synchronous altitude, it would only be about 100 kilometers wide. That's still impossible. We would have to completely deplete all of Earth's hydrocarbons in order to make enough Kevlar to do that. But we've gone from 170 times the diameter of the universe to 100 kilometers in diameter just by making a factor of 10 improvement in the specific strength. If we go another factor of 10 to the region that carbon nanotubes can do, we're talking taper ratios on the low order of 3. The tether itself would basically look like a tape measure. One of those roll-up tape measures that you can wear on your belt. That's the kind of thickness we're talking about from carbon nanotube-based space elevator. So it is incredibly sensitive to this parameter, the specific strength, the strength to weight ratio, which is the ultimate tensile strength of the material in pascals to the density in kilogram meters per cube. Now, for those of you who are dimensionally who are savvy with your dimensional analysis, you may notice that specific strength, this incredibly critical property that tells us everything we need to know about the elevator, which, by the way, we call a URI, the unit of specific strength. Pascals per kilogram meter cubed is what we call a URI. Can also be expressed as a speed squared, as meters squared per second squared. And it's tempting to ask, as one does in dimensional analysis, does that speed have physical meaning? And it turns out it It does, in a really, really cool way. The reason I'm wearing this rubber band on my wrist is not so I can punish myself if I make a faux pas. It's because it's an excellent demonstration of this principle. So rubber, to a first order, and I mean very first order with this analysis, has an ultimate tensile strength of about 10 megapascals. So if I were to stretch this with a stress of more than 10 megapascals, it would break. And its density is about 1,000 kilograms per cubic meter. So the specific strength comes up to the equivalent of about 100 meters per second squared. Turns out that velocity is the velocity, approximately, the rubber band will be going if you stress it and let it go. It ends up going at about 100 meters per second. That is the speed the material will go if you put all of its elastic energy into its kinetic energy. Which also means, if this were not a rubber band, if this were a carbon nanotube band, doing this would require about the force of a 747 engine, just to retract it like this, and doing this would blow me back as it exploded at Mach 20 on its way to orbit. So don't, if you ever have the chance to handle carbon nanotube elastic band, don't do that. You'll kill everyone with the arrow shot. But that just shows how much of a difference the specific strength of carbon nanotubes can be. You could launch this to orbit just by doing that. So that's kind of just a fun dimensional aside into what's represented by this specific strength. So then going back to the way this equation works, if we break out the proportionalities that only have to do with the planet, and we remember Mars is about 1/10 the mass of the Earth, and it's about 1/2 the radius of, and its radius is about 1/2 that of Earth. When we put those two factors together, we can determine that a space elevator is about 200 times easier to manufacture on Mars than it is on the Earth. Now, 200 times more feasible when the initial startup is wildly infeasible still means infeasible. But if it is getting more and more feasible every day as material science gets better and better and better, it means that the critical feasibility criteria will be met on a place like Mars before it is met on a place like Earth. Here's a graphical representation of the same principle. What I've done here is I have plotted the taper ratio of the elevator as a function of the material strength that we can accomplish with carbon nanotubes for Mars and for Earth. And I represented what the total mass of the tether would have to be at very specific strengths. So for something like what we can currently manufacture with carbon nanotubes, we're looking at a taper ratio of about 4. And we're looking at manufacturing about 3,000 tons of carbon nanotubes, which we can't do yet. But that is way more feasible than the 1 million tons of carbon nanotubes and a taper ratio of 1,000. And speaking to carbon nanotube experts, they're fully confident we can reach more than 32 mega-area specific strength in carbon nanotubes sometime in our lifetimes. So even at that point, it still remains way more feasible to manufacture a carbon nanotube-based space elevator on a planet like Mars than it is on a place like Earth. So let's put some actual numbers then to that. What does that mean for manufacturing the tether? So let's make some no magic assumptions here. We're going to only assume what we can actually do with carbon nanotubes right here, right now. Now currently, we can't manufacture carbon nanotubes in bulk at anywhere near the strength we can manufacture them on the micro scale. Manufacturing them in bulk means grouping them together into yarn bundles, which are much, much weaker. But if we run through those assumptions and then make a comparison between Earth and Mars, we're talking a difference between $4,000 trillion and $20 trillion. Infeasible. No one's going to invest $20 trillion in doing this, but as the carbon nanotubes get better and better and better, it rapidly falls to 10 trillion, 1 trillion, and then eventually when we reach the limit of carbon nanotubes, we're talking $10 billion or so. That's a lot of money, but it's more than enough money. It's not so much money that we wouldn't consider investing it as an infrastructure investment to reduce the cost of shipping materials off of the planet Mars. And where do the so what are the what are some of the other advantages that we would get from building it on Mars? Well, for one, no hurricanes. The wind loading on Mars is effectively negligible because of the thin atmosphere, unlike on Earth, where due to the fact that you have to build on the equator, you are always at a risk of hurricanes or typhoons. is the lack of lightning strikes. Carbon nanotubes are highly electrically conductive, so the entire space elevator was basically a lightning rod. You don't have to contend with that on Mars. There is the lack of ionization due to atomic oxygen in the upper ionosphere. And most importantly, there's no one living on Mars at the moment. If you were to build this on Earth, anywhere on Earth, you would have to contend with the concerns of people living there, that they're going to have this enormous structure, changing the location that they live, and objecting to its presence, its risk. That you don't have that problem on Mars because no one lives there. So it is an experiment like this might be way too audacious for Earth without a prototype, a demonstration, a proof of safety in a place like Mars where if something goes wrong and forbid it falls over, we're not going to injure anyone. And conveniently, Mars offers us the perfect place to do this. This is Pavonis Mons. It is the third highest mountain on Mars, and it is right on the equator, which of course is where we need to build the space shuttle. Pavonis Mons. Yeah, so on Mars, we have Olympus Mons, the tallest one, and then the three Prince volcanoes off the side, Pavonis, Arceus, and Astrius. And they represent the fourth, fifth, and fourth, third, and second tallest mountains on Mars.
Did you say volcano or not?
It's a former volcano. All the volcanoes on Mars are extinct now, so they're effectively enormous. So where's the cost incentives to do this? Well, if we assume that Mars is going to be serving the economic reason to colonize Mars is because Mars offers easier access to the resources that Earth would normally provide to places like the asteroids, to the moons of Jupiter. It is an easier way to get organics and nitrates, carbon, the kind of things that you normally need a planet to provide. And it's an easier way to provide this to the rest of the solar system than Mars is going to be operating as an export economy, an exporter of mass-intensive things, unlike Earth, which is probably going to be exporting less mass-intensive things, like robotics, computers, high technologies, that kind of thing. And every one of those destinations, adding a Martian space elevator drastically reduces the cost of shipping because you can affect all of the delta V for planetary escape with electrical systems. So the cost reduction is significant to pretty much every destination in the solar system that we want to go to, just by letting go of the tether. A couple of potential issues, though, that would crop up is we do conventionally assume that the space elevator would have to be powered by solar power. The climbers would be climbing the tether with mechanical linkages powered by solar arrays that are dragging along behind them. And there is less solar power available on Mars, but conveniently, the reduction in gravity almost perfectly cancels out that reduction in irradiance. So a climber designed for an Earth space elevator would be almost exactly as effective on Mars because of the reduction of gravity. There's also the concern, something that Mars has that Earth does not, is Phobos. So Phobos is one of the two moons of Mars. It's the larger one. It's only about 25 kilometers across, but it is right smack dab on the equator, and it is right in the middle of the altitude band that the space elevator would have to be operating at. So here,
it's also like slowly coming apart too, so eventually Mars is going to have rings.
yes, but very, very slowly. We're talking geological timescales, hundreds of thousands to millions of years. In 100,000 to a million years, if we don't have the ability to arrest Phobos' descent and stabilize it, then we're doing something wrong with the system. So Phobos is very close to Mars, so close that it actually rises in the west and sets in the east because it's orbiting so quickly. But it is definitely large enough that we need to worry about it. If you don't do anything about it, it will plow across the orbit of Mars. It'll plow right through the space elevator approximately every 14 sols. However, there is a solution. It's a crazily audacious solution, but as near as we can tell, there's no reason why it can't be done. It was originally proposed by Arthur C. Clarke in a science fiction book, his 1979 book, The Fountains of Paradise. It's called The Twang. And what happens is, as Phobos starts approaching the elevator, we send a climber racing up the elevator at very high speed. And it causes the elevator to crack like a whip. If you time it just right, the oscillation passes right by Phobos, and the entire elevator basically dodges to the side with whole kilometers to spare.
4 kilometers.
Yeah.
That's
Now these oscillations, these side-to-side vibrations happen anyway. They're unavoidable in a structure this long and this slender and this unstiff. All you have to do is you have to tune the elevator properly by the way you time the launching of these climbers in such a way that the twang, the oscillation, arrives at the orbit of altitude of Phobos at exactly the right time. Now, on paper, this seems insane. However, it's important to remember that we are dealing with very simple Newtonian physics here. It is possible to predict the position and the arrival time of Phobos on the order of meters and the timing of milliseconds if desired. This is classical Newtonian mechanics. This is the perfect situation for very high precision numerical modeling to be incredibly accurate. So if we can do the American air traffic control system, for example, where we're regularly scheduling thousands of flights to the order of seconds, there's no reason in principle why we couldn't do something like this.
And that would affect the stationary, what is it called, the middle part there?
The station? Not really, because the geostation can be as massive as you like. That's where you'll locate the facilities for deploying geostationary satellites, accommodations, hangars, that kind of thing. So if this ends up being significantly more massive than the tether, then it's basically a fixed point. It's like if you're jump roping, when you hold the end of the jump rope fixed, your hand doesn't move as the tether vibrates up and down. So you have to make the geostationary facility massive in order for that to work. But if you do, then this oscillation just bounces back and forth and gradually dies out.
But it's every 14 days?
Every 14 days is a guaranteed collision if you don't do anything about it here. So I have a more detailed simulation of it here. This is actual orbital data of the position of Phobos. Yeah.
Sure. Why they like just make an angle and go back?
You mean why don't we just build the elevator like that?
No. And make an angle. Like when this thing create, make an angle and go back.
Yes, it will. It'll vibrate back and forth.
Not like go like the whole.
Oh, the whole thing in the first vibration mode. That will also happen. There are vibrations at each fundamental frequency of the elevator, but because the elevator itself, I mean, we're talking 20,000 kilometers long in this distance. We only need it to dodge by about 20 kilometers in 20,000 kilometers. It's much easier to do a local perturbation rather than a full perturbation that way at a precisely controlled time. Because the first mode, this vibration mode, has period on the order of weeks. Whereas a shorter wavelength mode like this is a period on the order of hours. It's much easier to control.
Just lasso it and all along.
Right along with Phobos? Well, some proposals have been, well, Phobos is very close to the synchronous altitude. Why don't we make Phobos our base station? Unfortunately, Phobos is also way too massive to move. If we have the power to move Phobos to the synchronous orbit altitude, we don't need a space elevator. We've got enough power to.
Fair.
I mean, why not like build to like a gate for Phobos?
Like a what?
A gate for Phobos and further like
a hole in the thing.
yeah.
So Phobos is not going to be at the same place or moving in the same direction at every time. So here in the next slide, I kind of show this. This is a track of 2 months worth of data of the tracks that Phobos will make through the elevator's keep out sphere. So Phobos doesn't pass through the same position every single time.
If we make a hole a section, the numbing.
It'd have to be hundreds of kilometers wide. It'd have to be a hoop hundreds of kilometers wide.
Yeah. That's better than I think that would be
It'd have to be a structure hundreds of kilometers wide that was also rigid. That's pretty difficult to do.
this move. From K10 to this move and such things.
I agree, but that's because we're used to thinking about modeling things like buildings and bridges, where the oscillations and the perturbations are very difficult to predict. This is simple Newtonian mechanics and orbital dynamics. We regularly predict orbital mechanics factors to milliseconds, to parts per billion precision, and are correct about it.
For orbit mechanics, okay, but I mean for mechanical, like for vibrations and everything, it's something.
It's a whole other level, but
Yeah.
On paper.
The physics work.
yes, exactly. There's
But the
Considering
mechanical,
these are the carbon nanotubes and stuff.
Mhm.
If that, it would be this mechanically, yeah, it'd be able to work.
Yeah. And if it doesn't, we do have an alternative if this doesn't work. It turns out that positioning it at the equator is much easier. But if you can't position it at the equator, it is possible to put the base on a mobile platform, think something like the Saturn V problem, and then carry it south by about 120 kilometers. If you carry the base south by 120 kilometers, then you'll never be in the envelope that Phobos passes.
that's what I'm talking about. Or make the same, like the same thing we can angle. You know, for every copy, just the same base, and just
You need to move it out of the way every 14 days or so, or every 14 sols, which is difficult. Because the thing has the inertia of several aircraft carriers. It's difficult to do. Not impossible, but that may be the solution. Moving it off the equator may end up being the solution if the twang doesn't work. So like I said, this is a rendering of 60 sols worth of data of the close passes, and in most cases, it misses. In most cases. So here's a spatial representation of it. This is the closest point that the surface of Phobos will reach on every pass. And in most of them, it doesn't come closer than 20, 25 kilometers or so. Excuse me. But every so often, it does come by a close pass, and every so often, it will also come into a full collision. So 4 collisions in a total of 60 sols. So in every one of those, you just need to devote one climber to a dedicated twang, and the elevator will just sidestep Phobos. And if you happen to be on that climber, lucky you, because you are in for quite a treat. Because it'll be quite a view. This is true speed. This is This is a ×1 rendering of what Phobos would look like passing by if you were on the climber that had engaged the dodge.
What simulator is this?
This is Celestia.
We need to skip this part on a climber?
You wouldn't want to see this? You wouldn't want to see something the size of Manhattan coming by with 4.
So yeah, we just did our mirror.
I don't know. I'd pay to see this. I'd pay to see something the size of Manhattan coming by at several kilometers per second. Yeah.
Max, from the human perspective being inside, how would you describe the wobble
You wouldn't feel it.
experience?
You wouldn't feel it. It has a period on the order of hours. It's no different. Wouldn't feel it for the same reason you don't feel the first order harmonics of a building, even though the building may sway 3 or 4 meters at its tip.
Does the carbon nanotubes have like fatigue factor?
We don't know. That's an excellent question, and we don't know.
Okay.
We have not built enough large-scale monolithic carbon nanotubes to establish their fatigue problem.
That's the first thing I think about is like, sure, but like, what's the impact going on?
Yeah, if they do have fatigue limits, then we're pretty much sunk. We have to go to material like chloronitrides, but we don't know yet. All we do know is they're very strong. They're incredibly elastic. They have an elongation at rate of like 15–20%, and they're incredibly electrically conductive and also somewhat reactive with atomic oxygen. That's about as far as we know.
And also just like other either space debris or like small like things. How would that be? Impacted?
Like any material, when you get struck at 3 kilometers per second, it doesn't matter what you're made of. The debris just goes right through. However, because of our ability to track pretty much any space debris We only need to design it to be resilient to impacts of structures about that big, and you can do that by making the tether itself, instead of a flat piece, you give it a curve, like a tape measure. And in that situation, if you make it like 500 millimeters across, a few microns thick, and curve in most directions, unless you're really unlucky and the material comes straight across, it will only puncture, not cut. So then, and you can send a repair climber down to rehatch the material with more carbon nanotubes.
Probably a robot.
Yes, definitely a robot. All the manufacturing would be robotic.
But with larger debris, even if you can track them, how would you avoid them?
Same way you would avoid photos.
So that with a fan.
Yeah, with a
That's
fan.
a lot of fans.
It is.
But then well, how much will it have to change? Because like it's already and it's turn on in motion. So like how much would you have to?
You have to model it. You have to come up with a very precise numerical model of all the fundamental modes of this, all the vibration modes of this structure. Couple it with an incredibly intricate model of all the debris that you were tracking. It's crying out for an AI solution personally, because there are so many variables and so many things to optimize. But again, because the physics are so simple, because it's just classical orbital mechanics, you don't have to deal with any of the more complicated stuff. Exactly, like atmospheric perturbations or stuff like that. It is a simple problem on a large scale, just one that requires a very precise and very intelligent numerical modeling.
And
However, what if? Just because we like to engage in disaster thinking, because sometimes it's fun to see stuff explode. What if it did fall down? What if it was cut? This is a simulation that I put together several years ago of what would happen if it was cut at its absolute worst point up here at the counter. Has anyone read the Red Mars, Green Mars, Blue Mars trilogy by Kim Stanley Robinson? This is what happens. The Martian separatists attack the counterweight and sever it like this. Now look, notice the time scale here. We've already gone almost half a day. The whole thing falls, and you'll notice it falls eastward. It starts wrapping around the planet.
It's wrapping?
Yep, one time.
Oh, there it goes.
One time around the planet.
This is in one day?
Grand total of almost half a day. Half a day.
So what's
Then
the policy on? Oh, there's plenty of time to evacuate.
Yeah, and then the planet would have a belt, just like a on actual globes. The equator would be a literal belt.
Would it be like emergency buckets?
You need to arrest the fall. It's kind of hard to do it. Again, this thing has the inertia of a super tanker. Now, fortunately, if the break happened at a lower altitude, only the material below the break falls. The rest remains in Earth orbit. The rest remains in orbit. This is the absolute worst case scenario. But on a space elevator, if you cut it, at the most probable location is if it gets cut by orbital debris, which is at low altitude, 300 to 1,000 kilometers. Only the part below him falls to the surface. The rest stays in orbit. Yep.
Yeah.
But it stays in orbit. It'll just rise to a slightly higher level. And conveniently, the lowest few thousand kilometers of the tether, when it falls, doesn't fall very quickly, subsonically. You would, for the first few kilometers or so, you would be able to run alongside it and watch it fall. It's only after it reaches the end of its fall that it starts going hypersonically and actually doing a lot of damage. So, in reality, what would happen is if the tether started falling like that, we'd intentionally break it apart. We'd break it apart into smaller pieces, like the scuttling charges or something like that, and it wouldn't pose a hazard to the ground. So, in summary, we're nowhere near the point where we can build a realistic space elevator on Earth or Mars. Material science isn't there yet, but it's getting there. And the feasibility criteria is a cube of an exponent. So it becomes much more feasible, much more quickly with just incremental improvements to the state-of-the-art material science. It is mostly a problem of scaling up manufacturing and production. And it's very hard to predict when and where that will happen, but we saw it happen with the silicon industry, with the computer revolution. We increased our output by a factor of 10 to the 6. So it may very well be possible to do it with carbon nanotubes as well. We will have to wait and see. I I don't know when to expect it to be feasible. Sometime this century is really the best that I can say. But if it turns out that it is feasible before Mars, or if it turns out that Mars has a demand for an export economy before it becomes feasible on Earth, long after it will become feasible on Mars, economic incentives argue that the best place to manufacture it, the most profitable place to manufacture it, one where will be the strongest incentives to manufacture it, will be a place like Mars rather than a place like Earth. Thank you.
I have two questions. First one is, what about the moon? The second one is, are there any, well, I know ISEC are doing work on this, but are there, is that how do you say, like an accredited kind of research thing, or are there any, real deal research guys looking into this? Or?
ISEC is the closest, but this is, because there is zero money in something like this, space elevators tend to be a thing that old people do once they retire from their professorships and want something to keep themselves amused at. Like I am the young one in the room when I go to conferences on space elevators. So if you mean industry research in this, not really. There are 2 or 3 firms in Japan that I know of that are interested in doing this.
Any universities? Research institutions?
There are professors at universities that will engage in this research, but in terms of actual practical drives to make this kind of thing economical, not really. Now, there is a lot of really great research going on in carbon nanotubes because they have a wide range of useful applications long before anything this big. A former ISU alumni, Gadika Renić, does anyone know him? He's a former ISU alumni. He's the guy who I talked to get some of my numbers on CNT manufacturing costs. He's founded a company in India called Nopo, where they are manufacturing bulk carbon nanotubes for other purposes, so thermal protection, insulation, mechanical protection, hydrophobic properties, because they have a wide range of useful properties beyond their high strength to weight ratio. So there is that research, but it's not being driven because we want to build a space elevator. It's being driven because it has many more useful properties, and a space elevator will be a happy side benefit of it. As to your first question, why not the moon? The moon doesn't need anything as primitive as this. The moon has a much more advanced and easy way to get materials off the surface with an electric rail launch. A space elevator is only really necessary in a planet that has an atmosphere, because you can't go Mach 20 on the surface of a planet. If there's an atmosphere, it'll burn up. So you're absolutely right, it is 1,000 times easier to make a space elevator on the moon than it is on Mars. We could do it with Kevlar, but there are much easier ways to launch stuff from the moon with a 20-kilometer rail instead of a 100,000-kilometer flexible structure. So we could do it on the moon, but I don't think there is a reason to do it on the moon when there are much easier ways to get the benefits of an electric launch without the need to build something as primitive as this.
Great. Thank you.
Any other questions?
Would it be concerned to me, what do they call Earth has J2 effects, Mars has different because of the non-spherical,
Both Earth and Mars have similar J2 quantities because they're both rotating at about the same speed and are made of similar stuff. Mars does have much larger J3 and J4 perturbations because of the Tharsis bulge. The Tharsis mountains the Tharsis bulge that Olympus and the 3 Prince volcanoes are on top of. Mars has much higher J3 and J4 perturbations than Earth does. But again, that's all just higher order terms that you need to include in your numerical modeling, and it means the elevator won't adopt a perfectly straight up steady state configuration. It'll bow a little bit to the north due to the attraction of the Tharsis bulge. Yeah.
So I'm linking on the prediction that I just are there enough material enough people
carbon?
Oh, so not yet. We don't have the manufacturing capacity to do it. But on Mars, under realistic assumptions, so this is this is a no magic assumption. Under realistic assumptions, sometime 30 to 40 years from now, we're talking about 1,000 tons or so of carbon nanotubes. So enough nanotubes to fill this room. That's a lot. That's way, way more than we manufacture now, but there's definitely sufficient carbon to do it, especially because we don't manufacture it from the planet itself. We manufacture it in space from something like a C-type asteroid.
And this material is like that.
Very elastic, yeah. Like it's about 15% elongation at rate.
And what fits the material with Mars?
What do we get?
And what the thing that make the material fits with Mars?
So it's you mean like what does the factory look like? What do the reactors look like to make the material?
No, I mean to make an elevator, you need with an elastic material. You need something to hold the material, right?
Mm-hmm.
It's kind of
Counterweight.
what is it?
Counterweight.
Like, how is it attached?
Yeah, to Mars.
Oh, you mean how does it adhere to the surface?
Yeah.
If you do it right, if you build the structure to be in to be in equilibrium, the net forces here at the surface are actually zero. So it doesn't actually attach to the surface. It comes to the surface and then hovers.
I mean that thing.
The counterweight?
Yeah, what is it?
So the counterweight is something that you're allowed to pick the mass up. Without a counterweight, this function will just continue tapering to zero at infinite length. Your elevator would never come to a terminus. But if you cap it with some surplus rock or something like that, you can cap the elevator at a fixed length. Because in practice, there's going to be some fundamental limit to how thin we can make the ribbon before it becomes infeasible or it becomes a risk of being severed. And in this case, in the elevator that I'm talking about here, it's a rock 6 meters across, so like the size of this.
Seems so small compared to the scale of everything else.
Yeah. In theory, you can make the elevator as short as you want, right down to the synchronous altitude. Just your counterweight mass goes to infinity.
When the elevator comes, the universe thing, the energy you move on the average very fast, right?
Mhm.
So anything happen, all the elevator will be right? Like we assume that some degrees, pollution, or anything happen there, the
What happens to the elastic energy in the breaks?
yeah.
It goes into vibrations in the remaining pieces. Just like if you take a strand of take something rigid but brittle like a piece of spaghetti, a piece of uncooked spaghetti, and you bend it, and then it breaks. When it breaks, you'll see other pieces go pew, pew, shooting off in different directions. Same thing would happen if the tether disintegrated. The elastic energy would go into the debris.
What is the inclination of Mars?
You mean the equatorial inclination?
Its rotation with regards to its compared to its revolution.
Compared to the plane of the ecliptic?
Yeah.
About 23 degrees, very similar to the Earth.
Sure, sure. Okay, so if you have an elevator on the equator, Martian equator, then you can't launch towards the Earth.
You can twice a day.
Twice.
Once a day. Yeah, all you need to do is let go somewhere in this region, somewhere around 51,000 kilometers above the surface of the Earth, and do it above the surface of Mars, and do it at the right time. You'll end up on a elliptical orbit with periapsis at 180.
Okay, but what about is there a launch window?
Yes, there is. Same as interplanetary launch windows in a conventional
So
sense.
26 months, and so every 26 months you have around 1 month
Yes.
where you can launch it around once a day.
Yes. Now that's for the minimum entry velocity criteria. You can do it at any time of the year. It just means you end up because you have to let go at a higher altitude at a higher exit velocity, and you will arrive at Earth with 10 kilometers per second of surplus velocity, which is an impossible entry window to make. But Mars's primary exporting partner is probably not going to be Earth. It's probably going to be the asteroids, where you have a considerably wider range of opportunities to export to.
I think there's another lecture coming.
All right. Well, thank you very much for coming.
Thank you.